Hello, everyone, and thank you for your time and listening in today. My name is Aiden, and I'm going to be taking the next 10 minutes or so to go over one of Zupt LLC's newly developed technologies that we call HaloCAM. Before we get too into the details of HaloCAM, I do need to give you about 1 minute of background on our company and what we do. Then I'll be able to better explain what HaloCAM is, its applications, and how it works. Zupt is an engineering company that utilizes our own surveyors and engineers to develop and offer as a service efficient technology for primarily survey-based operations. Our technologies and services typically involve the efficient use of inertial measurement sensors, either as a standalone solution or with other aiding sensors tightly coupled with the inertial navigation solution. Our day in and day out work comprises of using our purely inertial sensor called CPINs to complete spool piece and jumper metrologies for the oil and gas industry. We do also have other inertial applications for offshore subsea survey, onshore high production flagging, 3D modeling, and subsea vehicle navigation. To start off with the sensors that we've developed, 3D Recon is our recently developed 3D modeling system. It utilizes 3 cameras and an inertial measurement unit in a subsea housing to provide both a precise real-time navigation solution for an ROV, as well as a geospatially correct, high-resolution point cloud model of what it images. For our next sensor, if you're familiar with Ixblue's fins or Sonardyne's Sprint, Halo is our compact 4,000 meter rated inertial navigation system with a Doppler velocity log option to be tightly coupled both physically and on a software level. The reason that I needed to bring up both 3D Recon and Halo is because HaloCAM has been developed from the knowledge we gained from both of those sensors. We had been asked if 3D Recon could be mounted to an ROV, sit 2 to 3 meters from a conductor casing being spud into the seabed, and automatically, in real time, determine the verticality and position of the conductor casing without pausing the jet in or having to physically mount brackets to the conductor casing. Of course, our answer was yes, we can do this, but we thought that 3D Recon, our 3-camera system, was a little bit overkill for that specific task. HaloCAM is 1 camera instead of 3, and inside of the subsea housing, we have a very good inertial measurement unit. Now we have a capable tool with a camera and a navigation solution. To develop HaloCAM, we took a DVL-equipped Halo nav, removed the DVL from the bottom end cap, and plugged in a single camera similar to what we're using in 3D Recon. So what does HaloCAM actually do and what is it used for? As I mentioned before, HaloCAM's intended application was determining the verticality and stick-up height of a conductor casing being spud into the seabed. However, with machine vision and inertial navigating capability, HaloCAM can accurately determine the attitude and differential depth of a target sticker placed on any subsea structure. The installation for conductor casings, structure piles, and wind turbine generator piles are conventionally completed by mounting bracketry for subsea gyros or acoustic buckets, acoustic transponder buckets. This, of course, means installing and recovering those brackets by the ROV or in a moon pole by a person. This is a time-consuming and unnecessarily dangerous task that we believe should be done with a simple and standalone sensor. Our vision is that a single HaloCAM can be installed onto an ROV for longer periods of time. The ROV then can simply sit a few meters away from the structure where we can clearly view the target. The positioning data is then processed and provided to the topside user in a simple user interface that provides real-time data at 5 Hertz. How does HaloCAM work? We have a waterproof and adhesive target on a structure, and the camera sees that target. We then combine machine vision image data and the IMU data inside of the housing that now allows us to tell you where the target is, what the attitude of the target is, and if you tell me where the ROV is via USBL or LBL positioning, I can tell you the absolute position of the structure. We use targets that some people will call QR codes. These are quite similar, but not exactly correct. It is what provides a large amount of redundancy in determining the attitude and position of the structure. The targets are available as large stickers or on consumable hardware that can be easily removed subsea. We wanted to make sure that was a benefit of our system. We do not have any issues with having the target placed on either a flat or gently curved surface, such as a 36-inch conductor casing. Out of the top end cap is a pressure transducer and a single subsea connector for interfacing both serial communications and power. Our power requirements are 24 volts, 75 watts, and we run our serial communications through RS-232 at a 38 forward baud rate. If we do decide that we also have to have the camera image data topside, we also have a 100 MB connection available. Zupt works closely with operators, tier 1 contractors, and other survey contractors that have told us their requirements for what is expected of a pile or conductor casing installation. The specs you see here on the screen are what we believe is capable with our current camera and the expected lighting from an ROV when we view from an offset of 2 meters away from the structure. Of course, the further away we are from the target, the more our accuracy will degrade. Another capability, if we have LBL positioning on the ROV, is the virtual positioning of touchdown points for buoy set placement. While we have opinions on the ability to accurately use virtual buoys to spud a well, we can bring in LBL ranges or lines of position into HaloCAM and determine a point for the physical buoy pattern to be set. If LBL USBL is not available and the client requires absolute positioning of the structure, I can use a known subsea monument as a position. If we place a target into a known location like a transponder frame, as you see here on the screen, we can align our position to the known location. If we move away from that known location for up to 3 minutes and see a target on a structure being deployed, we'll be able to position it to within a meter. HaloCAM can be used to translate known positions to unknown structures being installed. You can think of these targets installed into a frame as transponders, even though they're just passive targets. For differential depth or stick-up height, we do not suffer from the same drift issues because we're using an internal high-resolution pressure transducer to aid the vertical channel in the INS solution, so we do not drift in depth. While I have been focusing on determining the attitude and positioning of piles and conductor casings, Halo can be used for structures that are not cylindrical. The data that HaloCAM outputs is relative to the targets we use and can offset to those to any point on a structure. For example, a hub reference face on a tree or manifold. We can stick the target onto a curved or flat surface and can manipulate the target size based on what it'll be installed onto and the available space for the target. Now, the main differences between HaloCAM and other machine vision technologies completing similar tasks is the tight integration of the IMU inside of the subsea housing. There is no need for Rovins, Octans, or Sprint on the ROV. Having the IMU and camera data fed into the same solution means that we do not have to measure offsets from the camera to an external ROV INS. The IMU we use is non-ITAR controlled and can easily be shipped internationally and mobilized offshore. We can interface with small ROVs, doesn't necessarily have to be a work class size ROV. There's no need to pause hammering to collect the survey data. And please don't forget, HaloCAM is a derivative of Halo, our ROV and AUV inertial navigation solution. When HaloCAM is not being used for structure positioning, HaloCAM can be used as the sole INS on the subsea vehicle. No specialized personnel are required. All of the data processing is completed internally, and the data provided to the user is only the structure's attitude and position. After we finalize our development and have some more time in the water, we will transition HaloCAM to being a sensor that is sent offshore for remote data collection anywhere that has a minimal bandwidth connection to the shore. That is all I have for you today. I do hope that I piqued an interest in one of our new technologies that Zupt has developed and you may be hearing about in the near future. If you have any questions regarding anything I said today, please do not hesitate to reach out at my email above. I would also like to quickly add a big thank you to the SUT for providing me the opportunity to chat and as well as a platform for others to present their innovative technologies. That's all I have, and have a great day.